Welcome to the deep dive. Today, we're tackling what feels like, well, a real paradox in enterprise AI.
Mm-hmm.
How do you get that cutting edge performance, the kind you see in massive cloud models into environments that are super constrained?
Yeah, like air-gapped systems. Or maybe just a small company server.
Exactly, without blowing your security or needing a supercomputer.
It's that classic tension, isn't it? The firewall versus performance.
Yeah.
You, our listener, you need top-notch accuracy, but you absolutely have to protect your sensitive data.
Patient records, legal docs, internal code.
Right, you can't just be sending that stuff off to some third-party API.
Yeah.
So yeah, we're diving into a technical report today that offers a kind of blueprint for this.
Okay.
They actually show it's possible to get what they call frontier-level performance using these really lightweight models, lean language models.
And the key technique.
It's called Retrieval-Augmented Reasoning, RAR for short.
Got it. And our main source is this technical report detailing that architecture. It's interesting, they fine-tuned it using synthetic data.
Derived from a very specific secure knowledge base, the NHS A to Z condition web pages.
So that gives us a really concrete, sensitive domain to see how this all clicks together.
And this isn't just theory, right? This is essentially an implementation guide for any organization needing its own internal AI expert.
Could be for medical triage, like in the example, or legal review, manufacturing troubleshooting.
Anything where you need that expertise kept totally in-house on-prem, keeping that data locked down tight.
Okay, so let's unpack the two big ideas that have really, boosted LLMs recently and that this research builds on. First up is reasoning.
Right.
We're talking about that step-by-step thinking, chain of thought, Kun-T, people call it. And that's how even smaller models can sometimes mimic the complex logic of the giant ones on certain tasks.
That's like the thinking part of the engine. And the second big power-up is, well, it's classic retrieval-augmented generation, or RAG.
Ability to look things up.
Exactly. The model searches an external knowledge base, your documents, basically to ground its answers. That's what really cuts down on hallucinations and it makes sure it's factually accurate, especially for domain-specific stuff.
So the big cloud models, your GPT-4os and Geminis, they combine RAG and reasoning really well.
They do, but there's the catch. You have to send your sensitive data out to use them.
And that's the exact problem this research tackles head-on.
Right. If you're air-gapped or just have strict data policies, the whole solution has to run locally, and that demands a lean architecture.
Okay.
And maybe we should clarify RAG versus RAR here. Standard RAG just gives the model documents.
Right, context.
But Retrieval-Augmented Reasoning, RAR, that's the specific technique where you fine-tune the small model on structured step-by-step reasoning traces that actually use that retrieved data.
Ah, okay. So it's not just getting the documents, it's learning how to think using them.
Exactly. That reasoning component is what elevates a lean model from just repeating info to acting like a real expert.
So the goal is a small model that thinks like a big expert specifically for its domain. They couldn't just feed it raw data then. They had to teach it how to reason. So tell us about the method they used. It sounds quite clever.
It is. So step one,
Yeah.
secure the knowledge base. They use that NHS A to Z corpus, about 1,000 medical documents.
Okay.
Now, very important caveat from the source, and we have to echo it. This system is purely a research prototype. It is not meant as actual medical advice. Understood.
Absolutely. Prototype only. Clear. But the really smart part seems to be the synthetic data generation.
Yes.
To train this small model how to reason, they needed more than just Q&A. They needed the whole thought process laid out.
Exactly. So they used GPT-4o, a powerful model, to generate 2,000 synthetic patient queries.
Okay.
And these weren't simple queries. They included demographics, they knew the correct medical condition beforehand, and crucially, the correct disposition.
Disposition meaning like what should happen next.
Yeah. Self-care, go see your GP urgently or straight to A&E. The right next step.
And they specifically engineered this data to be tricky, right? To reflect real-world messiness.
They did. They created 3 types of queries to really push the system's safety. You had your straightforward, basic symptom descriptions. Easy enough. Then the hypochondriac queries. These are tough because they mix real symptoms with unrelated complaints, lots of anxiety. The AI has to sort the signal from the noise.
Right, filter out the irrelevant stuff.
That's
And the
good.
third type sounds really important for safety.
The downplay queries. Yeah, this is critical. It models patients who minimize serious symptoms. Oh, it's probably nothing, but
And the AI needs to pick up on the actual red flags hidden in that casual language, not just mirror the patient's lack of concern.
precisely. So once they had these challenging queries, they needed the teacher.
The expert model to show the small one how it's done?
Right. They used DeepSeek R1, which is known for its reasoning abilities.
Mm.
They used it to generate these structured reasoning traces for each query using the retrieved NHS documents.
So that trace included everything, the query, the docs, the step-by-step logic?
Query, docs, the reasoning steps, and the final answer, the disposition. That whole structured output became the training material, the curriculum for the lean model.
Okay, so they had this perfect training recipe, thousands of complex, structured reasoning examples. But getting there created a massive practical problem, didn't it? An engineering hurdle.
Oh yeah, a huge one, computationally. Their first attempt, wanting full context, was to retrieve the entire relevant NHS documents.
Which sounds thorough,
Yeah. But it resulted in training examples that were, on average, over 74,000 tokens long. Just
Oh.
massive.
Okay. And training a, say, 32 billion parameter model on inputs that long.
You need serious hardware.
Yeah.
They reported needing 16 NVIDIA A100 GPUs, the 80 GB versions.
Right. And that immediately kills the whole lean local deployment idea for most organizations.
Exactly. It defeats the purpose. It's not lean if you need a cluster of high-end GPUs.
So this wasn't just a minor tweak they needed. It was fundamental to making it practical, making it affordable. How did they solve that? How did they shrink the data without losing the vital medical information?
The solution was pretty elegant. Summarization for scale. They figured, look, we don't need every single word in the document. We need the core knowledge.
Distill it down.
Right. So they used another model, Qwen 2.532b Instruct, to automatically summarize the NHS documents. And they shrunk them by an incredible 85%.
85%. Wow.
Yeah. So that average token length plummeted from over 74,000 down to just about 7,500 tokens.
Much more manageable.
Absolutely. And that single move made the whole training process affordable and feasible for local deployment on much less demanding hardware.
That's a key strategic point right there.
Yeah.
You don't always need the full raw text. Highly distilled, targeted knowledge can be enough to train real expertise. Okay, so let's get to the payoff. The performance results on predicting the medical condition.
Right, this is where it gets interesting. So the base 32 billion parameter model, Qwen 2.532b, with no RAG, just guessing based on its internal knowledge, only 38% accurate.
Okay, not great. What about adding standard RAG, just giving it the document?
That helped significantly. Accuracy jumped to 54%.
Better. But now, the custom-trained one, the Retrieval-Augmented Reasoner, fine-tuned on those specific NHS reasoning traces, what we're calling the domain-specific reasoner.
That one hit 56% accuracy.
Okay, hold on. 56%. That puts it right on par with GPT-4o, a vastly larger frontier model, which also got 56% when using ARD on this task.
Exactly.
So that domain-specific fine-tuning, learning how to reason using the retrieved docs, that's what closed the gap between the lean model and the frontier giant.
That's the finding.
But let's pause here for a second. Because 56% accuracy, well, that still means it's wrong 44% of the time.
Right.
In a medical context, that sounds pretty high. How did the researchers kind of grapple with that? The ethics, the practicality of deploying something with that error rate?
That's a really crucial point. And they didn't just look at the overall percentage. They focused heavily on the type of errors being made.
Ah, okay.
And what they found was their custom-trained, domain-specific reasoner was significantly better at minimizing the most dangerous errors, specifically the underestimation errors.
Underestimation, meaning telling someone it's less serious than it actually is.
Exactly. Suggesting self-care when they really need A&E. Those are the errors you absolutely want to avoid in healthcare.
Okay, tell us more. How did this custom model compare against a more general-purpose lean model, one not specifically trained on those NHS traces, when facing those tricky, difficult user queries?
Yeah, they compared it to what we can call the general-purpose baseline reasoner, S1.132b in the paper. And the custom one showed clear safety advantages,
How so?
particularly on those downplay queries, the ones where the patient minimizes symptoms. The general-purpose baseline model had over a 40% increase in those critical underestimation errors.
Wow, 40% more likely to get it wrong in a dangerous way.
Yes, much more likely to suggest self-care or urgent care when A&E was the correct, safer call. Our domain-specific reasoner, because it was trained on those NHS reasoning patterns, drastically reduced those catastrophic mistakes.
So the takeaway is,
For safety-critical applications, that domain-specific reasoning training isn't just a nice-to-have for accuracy, it's potentially non-negotiable for reducing the most harmful types of errors.
that's a massive insight. Okay, minimizing the worst errors is key. But, a 32 billion parameter model, even with summarization, still needs pretty decent hardware. Did they look at going even smaller? Like, could you run this on a regular laptop?
They did, absolutely. And this is really important for listeners thinking about cost and deployment speed. They explored distilling this reasoning capability down to much, much smaller models.
How small?
They got down to a 1.5 billion parameter model that only needs about 3 gigabytes of GPU memory.
3 digs. Okay, yeah, that's feasible on a good laptop or a very small, cheap server.
Totally. And remarkably, that tiny 1.5B model was able to maintain performance comparable to the original 32B baseline before it got the reasoning fine-tuning.
Comparable to the 32B RAG only baseline, you mean?
Comparable to the 32B non-reasoning baseline, actually, the one that only got 38% initially. So it needed the reasoning boost.
Hold on. How does a tiny 1.5B model, which fundamentally knows less internally, keep up? Is it just relying entirely on the retrieval quality? Kind of cheating.
It's not really cheating. It's more like being expertly guided. The data, especially in their figure 5 graph, shows something really interesting for these smallest models, the 1.5B and 3B ones.
Right.
Just adding R, giving them the documents, didn't provide much of a performance lift on its own for those tiny sizes.
Ah,
For models that small, the significant performance boost came almost entirely from the combination of RAG plus that specific reasoning fine-tuning.
so the RR method basically teaches the tiny model how to properly use the documents it's given.
Exactly. It turns that tiny model, which might be lost on its own, into an effective guided expert for that specific task.
And they didn't just build a retriever and a reasoner in isolation, right? They connected it all within a proper conversational agent.
Precisely. That's key for usability. They used a conversational front end, another Quinn model actually, that intelligently decides when and how to use retrieval as a tool.
So it's not just blindly retrieving on every turn.
No. For example, if you've been talking about headaches and then ask something ambiguous like, where can I buy them?
Right. Could mean anything.
The agent uses the conversation history to figure out, you probably mean headache remedies, refines the query, then sends that specific query to the retriever. It adds that layer of safety and context awareness.
Okay, so let's try and wrap this deep dive up. We've basically seen a blueprint here. You can combine RAG with these sophisticated reasoning traces
Distill that expertise down.
into a model that's surprisingly small, down to maybe 1.5 billion parameters.
Small enough to run locally, in secure environments.
And critically, without giving up too much ground on accuracy or, importantly, safety compared to the giant cloud models.
So what's the bottom line for you, the listener? Well, this ability to deploy high-performing, specialized AI agents completely on-premise, that potentially solves a massive headache for sectors dealing with sensitive data.
Finance, healthcare, legal, R&D.
Any of them. It sort of fulfills that promise of having AI agents working securely inside restricted environments. But there's a however.
Always a however.
The performance of this whole system, this distilled lean model, is ultimately capped by the quality of the teacher model used to generate those reasoning traces. In this case, DeepSeek R1.
Right.
Ah.
The student can only be as good as the teacher allows.
Pretty much. The source even noted that the limitations of DeepSeek R1 likely restricted how well the final lean model could predict the correct disposition, the next action.
Which leads us to a really interesting final thought, doesn't it?
Mm-hmm.
If the ultimate performance of these lean, secure AI models depends on the reasoning power of the large external model they learn from, what happens when an organization's specialized knowledge is so secret, so sensitive, that it can never be shown to an external teacher model like GPT-4 or DeepSeek R1 in the first place?
Yeah, how do you create truly cutting-edge, in-domain lean models under those conditions?
What's the next step? How do you securely generate that perfect private reasoning trace without relying on a big third-party expert you can't actually share your secrets with? That seems like the next frontier.